Now this example is one of the ones that's explicitly mentioned in the syllabus that you have to be able to prove. The wording here doesn't quite match the syllabus, but you need to recognise it as the same question. Use vector methods to prove that the angle inscribed in a semicircle is a right angle. What does this mean? Let me draw the diagram. Here's a semicircle. I'm going to pick a point somewhere on the semicircle and call it A. Let's call these points B and C. This and this are supposed to be at right angles. That's what I have to prove, that this angle BAC is a right angle. Well, let me label the centre of my circle, actually a semicircle, as O for the origin. That's useful for later. OA, following my normal convention, is little a. OB is little b, and OC is little c. Because these two might be ambiguous, it might help if we actually write it. Let OA be little a, OB be little b, and OC be little c. That's my standard convention. Now I want to show that this is a right angle, so I'm going to be using vector methods by showing that the dot product of this vector and this vector is 0. A couple more things we can notice before we start. These three vectors are all the radii of the same circle. A, B and C are radii, which means that their lengths are equal. We're going to need that later on. The other thing is, this is one straight line. It's a diameter. So B is the negative of C. B is minus C. Okay, well, let's try our proof. Let's look at BA and CA. Oh, sorry, I think I'm actually going the opposite direction from what I said before, but it doesn't matter. Let's go this way. BA dot CA. If I can show this is 0, I've achieved what I want. Well, BA is A minus B, and CA is A minus C. That's a standard way of getting from B to A. We go via the origin. Negative B plus A. Negative C plus A. Okay, let's expand those brackets. It's A dot A minus A dot C minus B dot A plus B dot C. Whoops, what happened to my vertical positioning there? B dot C. Now, A dot A is the length of A squared. C, remember, is negative of B. So this is, let me do it this way. Mod A squared. Now, if I replace C by the negative of B, because this is the same thing as saying, it's exactly the same as saying negative B equals C. Right, that's the same thing. So I'm going to replace C with negative B, and that's going to change this sign. So it's going to become plus A dot B minus, oh, wait a minute, dot product is commutative. I can write this one as A dot B plus, now, what happened here? Oh, C is negative B. So I'm actually going to change this one as well. May as well do it all at once. This C is also negative B. So it's going to become minus B dot B. And that's where most of the magic happened. That's mod A squared A dot B minus A dot B goes away. B dot B is minus mod B squared. But wait a minute, the length of B is the same as the length of A. The length of B is the same as the length of A. So this is mod A squared minus mod A squared. Oh, look at that. Something minus itself. It's 0. What have I shown? I've shown that this vector dot product with this vector is 0. And that means they're perpendicular. Therefore, BA is perpendicular to CA. And that's what I had to prove, that this angle here at the edge of the circumference of the semicircle is a right angle. So I'm done. QED.